It is not advisable to simply change the capacitor bank to 30 kVA if one of the two large AC units is removed. The primary function of a capacitor bank is to provide reactive power compensation. This compensation is essential for reducing the current flowing through power lines and enhancing the overall efficiency of the electrical system. The size selection of a capacitor bank hinges on the aggregate reactive power demand presented by the loads it supports. Originally, the 60 kVA capacitor bank was precisely calibrated to cater to the reactive power needs of both large AC units. However, removing one unit leads to a reduction in the total reactive power demand. Consequently, the existing 60 kVA capacitor bank becomes oversized relative to the remaining load. An oversized capacitor bank can trigger several complications. Firstly, it can lead to increased voltage distortion. Secondly, it can result in a reduced power factor. Thirdly, it can increase energy losses. Fourthly, it may cause potential damage to equipment. To mitigate these potential issues, it is imperative to downsize the capacitor bank to align with the reduced load. Opting for a 30 kVA capacitor bank would be more suitable for serving a single large AC unit, although a proper electrical study would need to be performed to verify the correct size. When addressing capacitor bank adjustments, several factors warrant careful consideration. Firstly, the existing capacitor bank specifications must be thoroughly assessed. This includes its voltage rating, capacitance, and reactive power output. Secondly, a detailed analysis of the remaining AC unit's reactive power requirements is essential. This analysis should account for the unit's operating characteristics under various load conditions. Thirdly, it is important to evaluate the impact of the capacitor bank on the overall power system. This evaluation should encompass voltage regulation, harmonic distortion, and system stability. Fourthly, any adjustments to the capacitor bank should adhere to relevant electrical codes and standards. These standards provide guidelines for safe and effective capacitor bank operation. Fifthly, it is crucial to consult with qualified electrical engineers or technicians. These professionals possess the expertise to properly assess the situation and recommend appropriate solutions. Sixthly, the selection of a new capacitor bank, if required, should be based on its compatibility with the existing electrical system and its ability to meet the specific needs of the remaining AC unit. Seventhly, installation and commissioning of the new capacitor bank should be performed by experienced personnel. This ensures proper functionality and safety. Eighthly, regular maintenance and monitoring of the capacitor bank are essential for optimal performance and longevity. This includes periodic inspections, testing, and cleaning. Ninthly, it is important to keep accurate records of all capacitor bank adjustments, maintenance activities, and performance data. These records provide valuable information for future reference and troubleshooting. Tenthly, consider the long-term implications of downsizing the capacitor bank. This includes potential future changes in load requirement or system configurations. The purpose of a capacitor bank in an electrical system is multifaceted, contributing to improved efficiency and stability. Firstly, it enhances the power factor. The power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is reactive, not contributing to useful work. Capacitor banks supply reactive power, counteracting the inductive reactance of loads like motors and improving the power factor. Secondly, capacitor banks reduce energy losses. Reactive current flowing through power lines causes increased losses due to resistive heating. By supplying reactive power locally, capacitor banks reduce the amount of reactive current that needs to be transmitted, thereby minimizing energy losses. Thirdly, capacitor banks improve voltage regulation. Voltage drops can occur when reactive current flows through the impedance of power lines. By providing reactive power support, capacitor banks help to maintain stable voltage levels, especially during periods of high load. Fourthly, capacitor banks increase system capacity. By improving the power factor and reducing reactive current, capacitor banks free up capacity on transformers, cables, and other electrical equipment. This allows the system to serve more load without overloading. Fifthly, capacitor banks mitigate harmonic distortion. Some types of loads, such as variable frequency drives, can generate harmonic currents that distort the voltage waveform. Capacitor banks, when properly designed, can help to filter out these harmonics and improve the quality of power. When deciding to adjust or replace a capacitor bank, several factors should influence the decision-making process. Firstly, assess the existing power factor. Measure the power factor at the load and at the utility service entrance. If the power factor is consistently low, a capacitor bank may be necessary or an existing one may need adjustment. Secondly, analyze energy consumption and costs. Evaluate energy bills to determine the cost of reactive power. If the utility charges a penalty for low power factor, a capacitor bank can help to reduce these charges and lower overall energy costs. Thirdly, consider equipment loading. Monitor the loading of transformers, cables, and other electrical equipment. If the equipment is operating near its capacity, a capacitor bank can help to reduce the load and prevent overheating. Fourthly, evaluate voltage stability. Check the voltage levels at various points in the electrical system. If the voltage is fluctuating or dropping excessively, a capacitor bank can help to stabilize the voltage. Fifthly, assess harmonic distortion. Measure the harmonic content of the voltage and current waveforms. If the harmonic distortion is excessive, a capacitor bank with harmonic filtering capabilities may be necessary. Sixthly, consider future load growth. Anticipate future increases in load and plan accordingly. A capacitor bank should be sized to accommodate both current and future reactive power needs. Seventhly, consult with qualified professionals. Seek advice from electrical engineers and power quality experts. They can help to assess the specific needs of the electrical system and recommend the most appropriate capacitor bank solution. Eighthly, evaluate different capacitor bank technologies. There are various types of capacitor banks available, including fixed capacitor banks, automatically switched capacitor banks, and active harmonic filters. Each technology has its own advantages and disadvantages. Ninthly, consider the cost effectiveness. Compare the costs of different capacitor bank solutions with the potential benefits, such as reduced energy costs, improved equipment loading, and enhanced power quality. Tenthly, ensure compliance with standards. Make sure that the capacitor bank complies with all applicable electrical codes and standards. Installing a capacitor bank or modifying an existing one requires careful planning and execution. Firstly, conduct a thorough site assessment. Inspect the electrical system to identify potential locations for the capacitor bank. Secondly, select the appropriate capacitor bank size and type. Choose a capacitor bank that is properly sized to meet the reactive power needs of the load and that is compatible with the existing electrical system. Thirdly, obtain necessary permits and approvals. Comply with all applicable local, state, and federal regulations. Fourthly, install the capacitor bank according to manufacturer's instructions. Ensure that the capacitor bank is properly grounded and protected against overcurrent and overvoltage. Fifthly, commission the capacitor bank. Test the capacitor bank to verify that it is operating correctly and that it is improving the power factor and voltage stability. Sixthly, monitor the capacitor bank performance. Regularly check the capacitor bank voltage, current, and temperature to ensure that it is operating within its specified limits. Seventhly, maintain the capacitor bank. Perform periodic maintenance such as cleaning and tightening connections to ensure that the capacitor bank remains in good working condition. Eighthly, train personnel. Provide training to electrical personnel on the proper operation and maintenance of the capacitor bank. Ninthly, document the installation and maintenance. Keep detailed records of the capacitor bank installation, maintenance, and performance. Tenthly, review the capacitor bank performance periodically. Evaluate the performance of the capacitor bank on a regular basis to ensure that it is continuing to meet the needs of the electrical system. Downsizing a capacitor bank involves a systematic approach to ensure the electrical system operates efficiently and safely after the removal of a significant load, such as one of the two large AC units initially served by the bank. Firstly, perform a comprehensive load analysis. Before making any changes to the capacitor bank, conduct a thorough analysis of the electrical load remaining after the AC unit's removal. This analysis should include measuring the actual reactive power demand under various operating conditions to determine the appropriate size for the new capacitor bank. Secondly, calculate the new reactive power requirement. Based on the load analysis, calculate the new reactive power requirement of the remaining AC unit and any other connected loads. This calculation will determine the kVA rating needed for the replacement capacitor bank. Thirdly, select the appropriate capacitor bank size. Choose a capacitor bank with a kVA rating that closely matches the calculated reactive power requirement. It's generally better to slightly undersize rather than oversize the capacitor bank to avoid leading power factor conditions which can be detrimental to the electrical system. Fourthly, consider the voltage rating. Ensure that the voltage rating of the new capacitor bank matches the voltage of the electrical system. Using a capacitor bank with an incorrect voltage rating can lead to equipment failure and safety hazards. Fifthly, evaluate the impact on power factor correction. Assess how the downsizing of a capacitor bank will affect the overall power factor correction of the facility. The goal is to maintain a power factor close to unity, typically between 0.95 lagging and 1.0, to minimize energy losses and avoid utility penalties. Sixthly, check for harmonic distortion. If the electrical system has significant harmonic distortion, consider using a capacitor bank with harmonic filtering capabilities. This will help to prevent the capacitor bank from being overloaded by harmonic currents and improve the overall power quality. Seventhly, review protection and control settings. After installing the new capacitor bank, review and adjust the protection and control settings of the electrical system. This may include adjusting overcurrent protection, undervoltage protection, and power factor control settings to ensure proper operation and safety. Eighthly, conduct commissioning tests. Perform thorough commissioning tests to verify that the new capacitor bank is operating correctly and that it is providing the desired power factor correction. This should include measuring voltage, current, power factor, and harmonic distortion under various load conditions. Ninthly, monitor performance. Continuously monitor the performance of the capacitor bank and the electrical system to ensure that they are operating efficiently and safely. This can be done using power quality meters, energy management systems, or other monitoring devices. Tenthly, maintain and inspect regularly. Implement a regular maintenance and inspection program for the capacitor bank to ensure its continued reliability and performance. This should include checking connections, cleaning components, and testing the capacitor bank's capacitance and insulation resistance. When dealing with capacitor banks, safety is paramount. Firstly, always de-energize the circuit. Before working on a capacitor bank, always de-energize the circuit and verify that it is de-energized using appropriate test equipment. Capacitors can store a significant amount of energy even after the circuit is de-energized, so it's important to take precautions to avoid electric shock. Secondly, discharge capacitors before handling. After de-energizing the circuit, discharge the capacitors using a suitable discharge tool. This will remove any stored energy and prevent accidental shock. Thirdly, use insulated tools and equipment. When working on or near capacitor banks, always use insulated tools and equipment to protect against electric shock. Fourthly, wear appropriate personal protective equipment. Wear appropriate personal protective equipment such as safety glasses, gloves, and insulated footwear to protect against potential hazards. Fifthly, follow lockout-tagout procedures. Follow proper lockout-tagout procedures to prevent accidental re-energization of the circuit while working on the capacitor bank. Sixthly, inspect for damage. Before working on a capacitor bank, inspect it for any signs of damage, such as cracked or bulging capacitors, damaged wiring, or corrosion. If any damage is found, do not attempt to repair the capacitor bank yourself. Contact a qualified electrician to perform the repairs. Seventhly, be aware of potential hazards. Be aware of the potential hazards associated with capacitor banks, such as electric shock, fire, and explosion. Take precautions to avoid these hazards. Eighthly, follow manufacturer's instructions. Always follow the manufacturer's instructions for installation, operation, and maintenance of capacitor banks. 9thly, get training. Get proper training on the safe handling and maintenance of capacitor banks. 10thly, keep the area clear. Keep the area around the capacitor bank clear of obstructions and flammable materials. Remember that modifying electrical systems should only be performed by qualified personnel who understand the risks and safety procedures involved.